Okay, so we are going to look at one example. Okay, we're going to look at one example. And the example they're going to do, so this is example number 1. Now, in the exam, if I specify that you have to use integration method, you have to use integration method to solve your problem. Okay. Right. So this example over here is a cantilever beam.
Would you do that though?
Hello?
Would you specify though? You just said that we could use.
Yeah. I will say that you have to use integration method to solve. If you don't use integration method, you have no marks.
Okay.
Or in the exam, when solving mole circle, if you use transformation equation, you get no marks. You have to draw the circle. Okay? So we have a cantilever beam. Right? So this is our cantilever beam. So this is point A. This is point B. And the cantilever beam is not like the load, sorry, it's not similar to what you see before. I will elaborate, okay? So this load over here, right, is not really a gradient load, or we classify as a triangular load. Because we will start from 6,000 Newton per meter, and we will end up with 18,000 Newton per meter. Okay. And this have a distance from here to here. It had a distance of 6 meters. Okay, it has a distance of 6 meters. So I want to introduce you, as I say, this is an example. I want to introduce you to boundary conditions. Okay, why boundary conditions are important? Hey, what is going on down here? It's me again. Go on, my bad. I don't know why it won't move. I need it for it to move. It still won't move. It is Microsoft. Okay, I will not move it. Okay. Now, when we had a break, before the break, we have the shear force equation in terms of C1 and the bending moment equation in terms of C1 and C2, right? So C1 and C2 are constant. Okay, and can be determined from boundary conditions. So the thing is, what do we mean by what is boundary condition? So for this case, you need to know your boundary condition. So boundary condition, there are 4 that I want you all to know, of 4 different types. Okay, and I want you all to label them this way. Okay. We always specify that the datum is on the left-hand side. Yes? And I already showed you why. Okay. So over here, x is equal to 0. On the right-hand side, x is equal to 6. Right? Because left-hand side is the datum. So from here, I want you to label in this sequence. Okay. V, M, theta, Y. Okay. Remember this sequence. V, M, theta, Y. Why is that? Remember what I taught you? The shear force, you integrate, you get what? Bending moment. That's why V and M. Then later on, if time permits, when we integrate the moment, we get the slope, which is equal to theta. And when we integrate the slope, we get the what? Displacement. Okay. So I want you to remember the sequence V, M, theta, Y. Whether we get to deflection or not, I don't know. Okay. Let's do this first. So V, M, theta, Y. Okay. For now, I want you to focus on V and M. Okay. Okay. Now, let's create boundary conditions. Okay. The shear force at point A is equal to 0. Okay. And the bending moment is equal to 0 at point A. Why? Okay. Why bending moment at A is equal to 0? If I remove the support at point B, what will happen to the structure? If we remove the support at point B, the whole structure will what? Rotate. Yes or no? And for this fact, moment is equal to 0. Opara, you understand or no? Opara,
Yeah.
you got it? Oh,
Yeah.
thank God. If you don't get it, we spend another half an hour. Unbelievable. You understand, yes? Now, so we have just formed what? Two boundary conditions. Boundary condition means we know the condition exists and is the true value. One boundary condition is when x is equal to 0, v is equal to 0. When x is equal to 0, moment is equal to 0. On the right hand side, when x is equal to 6, v is equal to v max. M is also equal to what? M max. What value they are, I don't know. We don't know. But we only know one thing. It's going to be at its what? Maximum. Okay. Why is that? Why is it at point B, the shear force is at maximum, the bending moment is at maximum? Anyone? Why? Why we say that? No? Why we say that? Because at point B is where failure will what? Occur. Are we clear? Failure will occur where both maximum, both shear force and bending moment are at its what? Maximum. Right? This case, we know it's at point B. Okay. Now, at point B, you can see that the bending moment is not equal to 0. Why? Because the structure is not what? Rotating, is it? The structure is fixed horizontally. Okay? Okay. So now we know how to form what? Boundary condition. Now, I'll give you another one. Let's say now our structure is simply supported. Okay? Let's say now our structure is simply supported. Okay? Point A, point B. So let's say this is x is equal to 0, x is equal to 6, v and n, v and m. So what is the boundary condition? At point A, is there a shear force? Yes. So it's not equal to what? 0. At point A, is there a moment? The answer is no. Why? Because if you remove the support at B, if you take this out, right? If you remove the support at B, the structure will what? Rotate. So for this case, we know that moment is equal to what? 0. Likewise, at point B, when x is equal to 6, right? The shear force, is there a reaction at point B? Yeah, there's a reaction at point B. So V is not equal to 0. But however, moment is equal to 0 because when you remove the support at A, right, the structure will what? The structure will rotate. Okay? So again, you can form how many? Two boundary conditions. How many unknown we have? Two unknown. Two unknown, two boundary condition is enough. Okay. If you have four unknowns, you need to have four boundary condition. Okay. So let's start with this. So now I taught you how to solve for C1 and C2. Okay. So the next thing that we are going to do is we are going to find the equation of the distributed load. Okay, so let me get back to our question. I hope to copy this thing again. And if I paste here, will it work? Hey, it works. Okay. So we are going to find the equation of the distributed load. Right? Now, if I were to draw our free body diagram, if we were to sketch our free body diagram, right? We know, right? We have an equation at By, or reaction at By. We know that. We also know there's a moment known as MB, right? Then we know there is an equivalent load. This is easy to find. The question is, can someone tell me what is this distance? I can tell you this, it's not 2L over 3. Right? It's not 2L over 3 because it's not a triangle. What shape is this? This is not triangle, it's flat down here, right? Down here is not flat. It's a trapezium, yes or no? So we don't know this position. That is why, right, we don't know this location. That is why is that one way to solve is use the integration method. Another to solve is use the superpositioning method. I'm going to teach you the integration method. Okay. So to solve this, we need to find dv over dx is equal to minus omega as a function of x. Now we have to determine omega as a function of x. Okay, so now I'm going to sketch a different graph. I'm going to sketch a different graph now. Okay, we're going to sketch. So this is your omega, and then this is your x. Right? So we know that over here is 6,000, 12,000, 18,000. Okay, so this is 0 and this is 6. Okay, and we know the equation or our distributed load will look, our gradient, our function distributed look like this. So now we have to find omega as a function of x is equal to what? Is equal to delta omega over delta x plus by 6,000. Why 6,000? Because that is where the y-intercept is. It intercepts at where? At 6,000. Okay. So the change in y, or the change in omega, is 18,000 minus by 6,000 divide by 2 plus by 6,000. Oh, sorry, not divide by 2, divide by 6. Okay. So this will be equal to 12,000 divided by 6. It's equal to 2,000. Sorry, you have to have an x down here. Right? 2,000x plus by 6,000.